Hello, I am Yuki Sato. I'll talk about our recent work on type-safe generation of modules. This talk is about type-safe program generation or multi-stage programming, which I will explain by an example. Suppose we have an ordinary program for computing the power like this. To make it a code generator, we insert a few staging constructs and write a wrapper function like this. This process is called staging. We then run the code generator with a static argument 5 to obtain this code. Finally, we run the resulting code with a dynamic input 3 to obtain the final result. The important property is that if the code generator type checks, then the generated code is guaranteed to type check regardless of the static inputs. As we have just explained, an important merit of the MetaML style program generation is static type safety, which implies well-scopekedness, namely, generated code has no free variables or ill-scoped variables, assuming there are no side effects. However, this property is not free. Code generation should be purely generative in the sense that generated code cannot be analyzed or decomposed. Also, assuming that our language has lexical scope, code generators can generate code of expressions only. Namely, code of types or code of declarations cannot be generated. But is this satisfactory? In practice, we do want to generate a source file with declarations, which correspond to modules in ML. What are modules in ML-like languages? They are building blocks for large-scale ML programs, such as Coq-Proof Assistant and MirageOS, a widely used unikernel system written in OCaml. Modules are separate compilation units and provide encapsulation by abstract types. They are extensively used in highly abstract programs, such as modular implicit and tagless final embedding for domain-specific languages. This work proposes multi-stage languages for generating code of modules. Inoue and others in 2016 first proposed a language to generate code of types and modules, and these two works proposed languages for generating code of modules and their concrete implementations. But as far as we know, this work is the first proposal for typed languages, which has nested modules, no problematic behaviors, and a precise definition of the type systems, and type-preserving translations. Let me explain by an example how we can use an ordinary module in ML. This module defines a set of integers with a membership function. It consists of two type declarations and a function definition of the membership function, which tests if the first augment L is a member of the second augment set. The detail of the code does not matter. Here, we have a module for integers with an equality function EQ and a functor makeSet. A functor in ML is a function over modules, and makeSet takes a module EQ as the element type, and returns a module for the set of the element type. Thus, we can abstract the element type from the set of elements by a functor. Now, we can apply the functor makeSet to the module into EQ. To obtain the module for the set of integers, which is essentially the same as the intSet module before. Similarly, if string EQ is the module for the string type, then we can obtain the module for the set of strings in this way. Programming with modules and functors is thus easy and useful to build large programs. However, there is a performance problem. Namely, each module is compiled separately, and the function call of eq.eq is an indirect call to the function eq in the int.eq module. Put differently, the module boundary remains after compilation. Our target programs use modules and functors extensively. For instance, program transformations in the Target Finder embedding are expressed as functors. Hence, we need to apply functors to a module many times. In MirageOS, each application, such as a web service, is a module, and is selectively loaded to the kernel, achieved by a functor application. We have found 10 times nested functor applications in the source code of the MirageOS, which degrades the runtime performance. In summary, module-based programming is highly abstract and beautiful, but tend to be slow. Our work solves the problem by code generation for modules. To explain our idea, let us first review ordinary staging constructs for code of expressions. In the programming language MetaOCaml, the pair of angle brackets is called brackets, which generate code of an expression. We can splice code into another code by this tilde operator, called escape. This is a familiar approach by Koji quotation, studied in Scheme and other languages. Finally, we can run the generated code by the run construct in this way. Now, we can explain how we stage programs with modules and functors. The double angle brackets generate code of a module, just like brackets for expressions. The generated value has this type, which means a code type for a module code. We can splice code of a module into another code of a module. We need a trick here, rather than using a splicing operator for module code. We use a combination of the $! Operator and the ordinary splicing operator for expressions, which will be explained in the next slide. Running code of a module is similar. RunMod is the operator for running a module, and as a result, we obtain a module in which the code of the module n has been inlined. Thus, we can eliminate the indirection overhead. Let me explain the trick in the previous slide. Namely, what is the $! Operator? Suppose x is the code of a module and we write this program fragment. Then $x denotes this module. Namely, the $! Operator turns code of a module to a module consisting of code values. Now, $x.inc denotes code of this function. Therefore, we can splice the code like this. We think that it is essential to be able to manipulate each element in a module, even if it is a part of code of a module. It violates the purely generative approach. However, we can guarantee type safety for our language. Hence, decomposing code of a module and extracting its component are safe operations in our language. Now, we can stage modules and functors. We add a few staging constructs to the int.eq module and make set functor, which is easy. By applying the functor make set dash to int.eq dash to obtain code of a module, and by running it, we get a module which has no indirect calls. In this work, we have designed two languages for generating code of modules. Both of them are based on Core MetaOCaml with code generation features. The language LambdaG has first-class modules in the generative style, while the language LambdaA has second-class modules in applicative style. The two styles are different when we apply the same functor f to the same module x more than once. In generative style, the type m1.t is not equivalent to m2.t, which means Funct application generates a fresh module. In applicative style, the two types are always equivalent. It is known that both styles have their own merit, and the current OCaml supports both styles. We extended the both styles to module code generation. LambdaG is a refinement of the languages studied by Watanabe and others, but has more features such as nested modules. LambdaA has not studied in the literature. The type system for modules in applicative style has complicated typing rules, and they interact with our dollar operator. It is our contribution to design a rigid type system for this language. For details, please read our paper. We have designed type systems for LambdaG and LambdaA. Here, we show a typing derivation for our previous example. The code of a module X is typed in this way, where mcode means the code type of a module, and this part denotes the type for modules. Following our principle, we can infer the type for $x.inc as code, where code is the code type for ordinary expressions. We can then splice this code, which has the type int to int. We have defined translations for our languages to play MetaOCaml. The basic idea of the translations are the same as the dollar operator. We translate code of a module to a module of code values. We need a trick here to avoid code duplication, when the same function in a module is called more than once. For this purpose, we add the generate primitive in MetaOCaml, which performs an optimal let insertion. Translating the run module primitive is not straightforward, as we have nested modules. See our paper for the definition. We have proved that our translations preserve typing. Thus, all code generators in LambdaA or LambdaG can be translated to play MetaOCaml. The proof is straightforward, and we stress that the difficulty was the definition of the precise typing rule for the dollar operator in the applicative style. We have implemented our languages using the translations, and conducted experiments for examples in the paper, embedded DSL in the tagless final style, and simple program transformations for DSL terms, such as this one. We have measured the performance of the program transformation in the tagless final style, and compared our implementations with existing works. The graph shows the execution time for 4 implementations. The horizontal axis is the number of Funct applications, and the vertical axis is the execution time in seconds. The results show that the generated module ran much faster than the naive, no generated one, and both of our two languages have slightly better performance than the existing work. Also, our two languages have quite similar performances. Hence, we can select a suitable style depending on applications without worrying about the loss of performance. We have not yet tested expressivity of our languages, which is left for future work. In this work, we have defined 2 languages for generating code of a module. The difference between the two is subtle, but not negligible in ML-like languages, as each one has its own merit and demerit. For each language, we have designed a type system and a type-preserving translation to play MetaOCaml, which was implemented. We have shown that our languages and implementations are useful for eliminating indirection overhead, and no-code explosion problem occurs. We have many future works as listed here. Thank you for listening. Questions are most welcome.